Okay, it's my pleasure to introduce Sarah Whitehouse, who's going to tell us about model structures and spectral sequences.
Okay, thank you very much, Niall. Thank you for organising, and thank you everybody for coming. So yeah, I'm going to talk about some model category structures that are related to spectral sequences, and the particular results that I'll talk about today are joint work with Jin Fu, Ai Guan, and Muriel Livenet. So here's a plan for what I'm going to talk about today. Firstly, I'll explain something about ER quasi-isomorphisms. So those are a kind of hierarchy of weak equivalences that you can think about, and they're related to the stages of a spectral sequence. And the particular context in which I want to talk about these today is multi-complexes. So I'll spend a bit of time defining those, talking about those, giving some kind of idea about why they're interesting. And then I'll present model structures on multi-complexes. I'll say a little bit about the ingredients that go into these model structures, and I'll end up by saying something about comparing the different model structures. Okay, so first the ER quasi-isomorphisms then. So there are some different contexts for this, and I'll mention a couple in a moment. But you want to think about some category C for which you have an associated functorial spectral sequence. So this means that for every object in your category C, you have a spectral sequence. So I'm thinking of that as the pages of the spectral sequence. So everything is in modules over some commutative ground ring. So the rth page, ER of A of the spectral sequence is, well, firstly, it's a bi-graded R module, and then has on it a differential on the R page. So it will have some bi-degree. My conventions will probably become clear as we go along. And I'm not writing all the data here. You obviously want the R plus first page to be the homology of the rth page with respect to the rth differential. And then you want this to be functorial. So when you have a morphism between A and B in your category, you have an induced morphism ERF on the R page of the spectral sequence. And again, I'm not writing all the data. The induced map on the R plus first page should be the one induced in homology by the one on the rth page, and so on. So there are quite a lot of different contexts where spectral sequences arise, of course, and where you might want to think about this kind of situation. So the ones that I've listed there are, well, firstly, filtered complexes, and then bicomplexes. And in both of those two cases, those are things that I've looked at with some other people in earlier work, and I'll mention a little bit about that later on. And then the third one that I've listed here is this category of multi-complexes, and that's the one that I'm going to focus on in this talk today. And I'll say exactly what I mean by that, what they are. They're also sometimes known as twisted complexes. So this is going to be the focus of this talk. Okay, and then you can see what a ER quasi-isomorphism should be, probably. So in any one of these categories where you have this associated functorial spectral sequence, you call a morphism an ER quasi-isomorphism if the induced map on the R page, the spectral sequence, is a quasi-isomorphism of these things, this R bi-graded complex. Or in other words, if the map at the R plus first stage is an isomorphism. So in that situation, this gives a class of morphisms which could reasonably be the weak equivalences of some model structure. So that class is closed under composition, and it contains all isomorphisms, and it satisfies the 2 out of 3 property. So we have this class of morphisms. We have one for each R, each non-negative integer R. and it's a weaker and weaker condition as R increases. So we have inclusions, as indicated here, larger and larger classes of weak equivalences as you increase R. And the game, if you like, is to find model structures for which these are the weak equivalences. And of course, another thing that comes into this is that you can think of the R page as a quotient of the R cycles modulo the R boundaries, and that fact is going to come into play when we describe these model structures. Okay, so that was about the ER quasi-isomorphisms, which are going to be our notions of weak equivalence. And then I want to say a little bit about multi-complexes. So I want to talk about the category on which I'm going to define model structures. So a multi-complex is, well, firstly, a bigraded R module, and everything is unbounded, so ZZ bigraded. And then you have a bunch of structure maps. You have a DI, which is a map from the A to A, with a certain bi degree. You have one of those for each non-negative integer I, and satisfying an infinite family of relations. So you have this alternating sum of di dj is 0, where I plus j adds up to a fixed L, and you have that relation for every non-negative integer L. So before going on, it's probably helpful to just write out the first few of those relations more explicitly to unravel a bit what this structure is. So that's what I've done here. The first of these relations is just that d0 squared is 0. So d0 is an actual differential. And then the next relation says that d0 and d1 commute. And then the next relation, so the case L equals 2 of this equation up here, this is if we write it out longhand, this is what it says. So it does not say that d1 squared is 0. So d1 does not have to be a differential, but d1 squared is the same as d0 d2 plus d2 d0. So if you think of d0 as your kind of underlying differential, then what this is saying is that d1 squared is a differential up to homotopy, with an explicit choice of that homotopy being given by d2. So that's what's going on for the first few cases of the relations. And so what we have is, well, an underlying differential, and then another thing which is kind of trying to be a differential, but it isn't actually a differential, it's a differential up to homotopy. And what the D3 and D4 and so on would be, that they're giving kind of higher homotopy coherences for this situation, for a differential up to homotopy. I can say something a little bit more about that in a moment. Okay, so just to go on really with the previous definition. So I told you what a multi-complex was. It's a bigraded module with these DIs satisfying these relations. And then I'll also discuss a little bit truncated versions of these things. So we might want to talk about an N multi-complex. So this would be a multi-complex where the structure maps, the DIs, are 0 from stage N onwards. So you just have the first few non-zero structure maps potentially, and then 0 for the higher structure maps. Okay, so that's in order to be able to think about kind of truncated versions of this structure. And then the other thing I should tell you about is morphisms. Yes, and it's convenient to think of the full structure of a multi-complex as being the case n equals infinity of an n multi-complex. So that's just a kind of notational convention that's quite useful. And then morphisms. So a morphism of one of these things is just, well, firstly a morphism of bigraded modules, by degree 0, 0, and just commuting with all of the structure maps. So that's what the morphisms in this category are. And then the last thing is just some notation. So we'll just write n multi-complex, NMC, for n multi-complex of R modules. So that's the category that we want to think about, or the collection of categories that we want to think about. We're going to think about these n multi-complexes for all n, including the case n equals infinity, which is the multi-complexes themselves. Okay. So let's just think about some special cases or examples, and I'll say a little bit about motivation for looking at these kind of structures. So firstly, some special cases. So if you just have a one multi-complex, so that means you just have a single structure map, you just have your D0, and all the higher ones are 0. So you've just got a bigraded module, and it's got a differential on it, D0. And with my conventions, that's a vertical differential, so it has by degree 0, 1. Okay, so that's what a one multi-complex is. And then a two multi-complex is a bicomplex. So at this point, we would have two structure maps, non-zero, D0 and a D1. And the relations now do tell you that, well, firstly, D0 is a differential, that's always the case. It commutes with D1. And now because D2 and above are 0, it is the case here that D1 is also a differential. So this is giving us the bicomplex. And then just to sort of come back to what I indicated earlier about sort of higher homotopy coherences, for D1 being a differential up to homotopy. And that's something that I'm saying in a more specific kind of way here in this comment. So this is one way you can think about what multi-complexes are. It's the homotopy coherent version of a bicomplex in the sense that's written here. So if you work in vertical bicomplexes, so just with your D0, an underlying category in which you just have a vertical differential, then you can say make this statement accurately using the language of operads. So you could make the operad of dual numbers. So that's an operad which just has a single generator, and it has a single relation which says that it squares to 0. So this if we just take the D algebras in vertical bicomplexes, the algebras will be bicomplexes. So we've put our D0 in the underlying category, and using the operad, we're putting in a D1 compatible with the D0, and which gives another differential, squares to 0. And then the statement about what multi-complexes is in this context is that it's a multi-complex is a D infinity algebra. So you build using standard operatic kind of machinery the infinity version of the operad, so the operad for the homotopy coherent version of the algebraic structure. And if you do that here for this example, then what you get is exactly a multi-complex as a D infinity algebra. So all of that is just to say that one way of viewing what this structure is as the sort of homotopy coherent version of a bicomplex. Okay, and then I wanted to say a little bit, only really a tiny bit, about the sort of history of this and where these things have come up, and who's been interested in them. So I'm not going to say a huge amount. The first place these arose, at least as far as I've found, is in work of Wall back in the 60s. And it came up there in thinking about resolutions for group extensions. So if you have a group G, which is an extension of K by H, and you're interested in building a resolution for G, calculating its homology or cohomology, then you can, there's a procedure which allows you to build such a resolution given resolutions for K and H. Then you can build a resolution for the extension group G, and the form of the resolution that's given in this work is that it is some kind of totalization of a multi-complex. So they're arising there as the form of the structure that you get on resolutions in this setting. So that's where they first came up, and then sort of building on those, well, the same idea appears in the approach taken by Guggenheim and May to differential homological algebra. So again, you want to build resolutions of things that are themselves differential objects, they're chain complexes or co-chain complexes, and this approach that's adopted there again uses multi-complex type resolutions. So they've come up in lots and lots of places, and I'm not going to try to mention all the names of people who've worked on them, but they're common objects because they arise naturally as resolutions in this kind of context. And then I wanted to skip a few decades and come a little bit more up to date and mention derived A-infinity algebras. So these were introduced by Stefan Sagava in 2010, and they can be thought of as a multiplicative enhancement of multi-complexes, or of the story that I was just talking about. So if you want to build sort of resolutions, not just of differential graded modules, but of differential graded algebras, then this is the kind of structure that arises. So that's roughly what a derived A-infinity algebra is. And every derived A-infinity algebra has an underlying multi-complex. So roughly one can think of the structure as some kind of combination of a multi-complex structure, so these higher DIs, and an A-infinity structure. So, the infinity version of an associative multiplication. And I mean, the reason I'm mentioning this is because this is really how I came across multi-complexes. I got interested in these derived A-infinity algebras and indeed in their homotopy theory. And if one's going to try to understand that, then you end up thinking about the underlying multi-complex structures. So that's how I got into thinking about these. Okay, so that was explaining what multi-complexes are and a little bit about why they're interesting and where they arise. Then the next part of the story that I want to tell is about the spectral sequence associated to a multi-complex, because we want to think about this hierarchy of equivalences that arises from thinking about that spectral sequence. So, so firstly, we do have an associated spectral sequence for every multi-complex. Goes via some kind of tote, so you build an associated total complex, which comes with a filtration, and therefore that puts us in a familiar setting where we have an associated spectral sequence. Okay, so it turns out that you can give really explicit descriptions of the structure of that spectral sequence. So given a multi-complex, it comes with all these structure maps, the DIs, and one can write down really explicit formulas for the associated spectral sequence. So one can describe the R cycles and the R boundaries and the differential on the R page of that spectral sequence. And I'm going to say a little bit more about this. So this is something that I did in joint work with Muriel Livenet and Stephanie Ziegenhagen. So there's just a short paper which gives these formulas, and I'm going to show you some of them, not all of them. Let me just say something about the R cycles and the R page differential, and I won't also tell you explicitly about the boundaries. I'll just say that one can write those down as well. So I want to talk about this a little bit. In just a moment or two, I will show you some pictures with some examples of what this looks like, so it might become a bit easier to understand what this is saying with that. So let me just talk about this a little bit first. So the zero cycles, that's just the object A itself. So the zero cycles for a multi-complex A, that's just A in the relevant bi-degree. And then the R cycles, well, so you have to specify an element A0, and then you require the existence of a bunch of AJs, which are kind of diagonally offset from the original A0, and such that a bunch of relations are satisfied. So there's a bunch of formulas, each of which says that some kind of alternating sum of dij is 0, where I plus j adds up to a fixed L, and you have R of these equations, relations that have to be satisfied. So I'll show you a picture for what this looks like in just a moment. In any case, you can specify these R cycles really explicitly by some formulas, and also the R boundaries, although I haven't written that. And then once you've done that, you can give a really explicit formula for the differential on the R page. And that's quite straightforward once you've done the other things. So the differential on the R page of the class of an R cycle is given by the class of some alternating sum of di's applied to those A's that I mentioned. Of course, one has to check some stuff like this is well defined and independent of choices and things like that. So let me show you some pictures to make this a bit more understandable, perhaps. And yes, this comment I should have made. So I gave formulas which were for the general multi-complex case, but of course you can just restrict to any of these truncated cases. So you can restrict to n multi-complexes. And if you restrict down to n equals 2, so where you just have d0 and d1, then everything that I've said here is sort of a really well-known description, explicit description of what's going on in the spectral sequence of a bicomplex. Okay, so here's my first little picture or example. So this is the bicomplex case. N is 2 here. So this is the bicomplex case, kind of as a warm-up, I suppose, to get us started. Here appear, well, which differentials do we have? So we're in the bicomplex case, so we only have d0 and d1. Those are the structure maps that we have, and the arrows indicate the conventions that I've got here for bi-degrees. So d0 is going vertically up, and d1 is going horizontally and left. Okay, and then I'm just telling you about the 3 cycles. So I've just picked a small, but not too small, an R, in order to show you what those formulas mean. And at the moment, this is just a bicomplex case, so this is a kind of well-known thing. I'm just showing you what it looks like. So what does it mean to have 3 cycle? Well, so the 3 cycle is going to be this element A0 here. And then the equations say, well, firstly, they say that D0 of it is 0. And then D1 of it doesn't have to be 0, but it does have to be hit by D0 of something. So there has to exist an A1 whose D0 is A1 of A0. And then similarly, we can think about D1 of A1, and it doesn't have to be 0, but there has to be some A2 such that D1 of A1 is hit by D0 of A2. So the 3 cycles was an A0 such that there exists an A1 like this, and there exists an A2 like this, satisfying these equations that I've indicated. And in that situation, the differential on this third page of the spectral sequence would be given by sending A0 to this class, or minus the class of this element here. So that's kind of a standard description of, well, in this case, 3 cycles for the bicomplex case. Let's put in a little bit more structure to just see what's going on. So if we think about now, still always 3 cycles, but think about n is 3. So in other words, I've put in 1 more of the structure maps. So D1 is no longer a differential, but it's a differential up to homotopy given by a D2, which goes like this. Then what changes in those formulas that I showed you was, well, now there's room for D2 in a couple of places, and the formulas sort of change accordingly. So we still have an A0 whose D0 is 0, and then an A1 just as before. But the first change happens here because there's room for a D2 of A0 here. So now A2 is required to be like this. So the formula for D0 of A2 is not just D1 of A1, but a difference between that and the new thing that can appear here. And there's a difference that comes in the formula for the differential as well. So there's another thing that can appear, which is a D2 of A1, and that appears in the formula for the differential on this element. And just one more, and at least for 3 cycles, this is sort of already the general case, because there's not room for any higher structure maps at this stage of 3 cycles. So if we put in now a D3 as well, there's just kind of one place in my picture where a D3 could appear, and it's this orange one that I've added in here. And so actually the description of the 3 cycles won't actually change, but the D3 makes its appearance in the description of the differential in that situation. So all of that was intended to just give you some kind of a flavor of what's going on. And it's also because I'll need to kind of revisit this and talk about a modification when I talk about the model structures that we have. Okay, so let me tell you about the model structures then. So here's the theorem that gives the model structures. So I'm giving model structures on this category of n multi-complexes, and I'm doing that, well, for every n between 2 and infinity, so from bicomplexes all the way up to multi-complexes. And I'm doing it for each r, each non-negative integer r, so that relates to the stage of the spectral sequence. So the n is how many of the structure maps you have in your category, and r is the stage of the spectral sequence that you're going to look at to sort of determine the model structure. So the statement is that you get a cofibrantly generated model structure. So the one on n multi-complexes for stage r, I'll denote like this. And well, so the first point is just that this does what we were hoping for. So the weak equivalences are the ER quasi-isomorphisms. So those morphisms which are inducing quasi-isomorphism on the R page, or equivalently an isomorphism on the R plus first page. Excuse me. So and then I've specified for you what the fibrations of the model structure are. So those are determined by surjectivity conditions. Namely, you get a fibration F whenever the morphism induced on the ICE page is surjective for every I starting from 0 all the way up to R. So surjective on every page of the spectral sequence up to the relevant stage that we're talking about. And I mean, the cofibrations are whatever they have to be, having the relevant lifting property. I'm going to say more though about, well, how we get this cofibrantly generating model structure. So something about the generating cofibrations and trivial cofibrations. Okay, so these are the model structures that we have. What I want to do is, well, firstly make some comments about them and then say a bit about the ingredients that go into them. Okay, so, well, firstly, you might wonder, what about n equals 1? Let me just go back for a second. So I said that I was specifying these model structures for every n from 2 up to infinity, so from bicomplexes all the way up to multi-complexes. You could think about n as 1, but it's kind of trivial case in some sense. So if you did n equals 1, you wouldn't find any difference between the R model structures. There's really just the R equals 0 model structure, because if you're doing the n equals 1 case, you just have the single vertical differential D0. Your spectral sequence just collapses already at the E1 page. So nothing happens with these different R's. The R's are all the same. All the structures that you're going to get are going to be just the R equals 0 structure. And that's a familiar thing. What we've got really then in this case is, well, these vertical bicomplexes. So that's just like having a cochain complex, unbounded, with a kind of extra grading that doesn't really change things. And this model structure is just the projective model structure on unbounded cochain complexes. So that case, you could do it this way, but it's not really interesting. And then for n equals 2, so the bicomplex case, so this is something that together with the co-authors listed here, I'd worked out previously. So we'd already done the bicomplex case and found, well, the model structures that are given here in the particular case of n equals 2 is something that I've done earlier with Joanna Cirizzi, Daniela Egas-Santander, and Muriel Libanet. So the multi-complex case that I'm talking about here generalizes some earlier work from the bicomplex case. And then the way this works out, there are kind of a couple of different variants of the model structure. So for fixed n and fixed r, you can describe Quillen equivalent model structures, so in a couple of different ways. The one I gave you in the theorem a moment ago characterized the fibrations by surge activity on the pages of the spectral sequence up to a certain stage. But you can also get one where the fibrations are characterized by surge activity on R cycles, or well, a variant of R cycles, which is going to appear quite soon. And indeed, the way we do things is that's the one that appears first, and then you get the one which is perhaps easier to describe with the surge activity on the pages of the spectral sequence as a consequence of this other one. Okay, so I want to spend a little bit of time telling you something about the ingredients that go into describing these model structures. So they're cofibrantly generated model structures. So there's kind of standard machinery, of course, for establishing the existence of such model structures. And what you do is you specify some sets of morphisms in your category, and you check a kind of standard list of conditions which tell you that those sets are the generating cofibrations and generating trivial cofibrations of a model structure. So that's sort of the general plan, and then you have to think about how you can actually specify suitable sets for those cofibrations. And then the other thing, somehow the key idea that comes into this picture, which was already the case in the bicomplex version, and it happens again here, is that in order to specify those sets I and j, you need representable functors, versions of R cycles and R boundaries. So the terminology that we use for these is the notion of witness R cycles, and so we write ZWR for the witness cycles, and also witness boundaries, so BWR for the witness boundaries. So the point being that you specify these objects, and in fact actually these objects and a map between them, in order to describe the generating cofibrations and generating trivial cofibrations in terms of these objects and maps in your category. So you want to, I have to tell you something about witness R cycles and witness R boundaries, and then the point is that these things are going to be representable functors, so they're going to be objects, so there's going to be an N multi-complex representing the witness cycles, and another one, this BW thing, some kind of map between them. I'm not going to go into all the details of this, but I'm trying to give you some kind of flavor of the constructions. And these are representing objects, so in the sense of mapping out of the corresponding object gives you the thing you want. So you map from the witness object for the R cycles in whichever category, whichever of these categories you want. So say in N multi-complexes, you take morphisms of N multi-complexes out of your witness cycle object, and that gives you the witness cycles. Similarly for the witness boundaries, and you do this, I mean, the criterion for this being the right thing, or at least a right thing, is that you do indeed recover our page of the spectral sequence as witness cycles over the image of witness boundaries. So you have the morphism on the objects, on the representing objects, goes the other way from witness cycles to witness boundaries. And then you apply the functor, and so on objects it goes from this BW thing into ZW, such that the quotient by the image is indeed the R page of the spectral sequence. So I want to try and explain a little bit more about these witness things without giving too many horrible formulas and the like. So, well, so for the witness cycles, I think it's kind of reasonably clear, sort of once you've absorbed the description of what the R cycles are for a multi-complex, it's reasonably clear what you should take to be the witness R cycles. So that's what I've written here, and I'll talk a little bit about that. And then I won't give you details for the witness boundaries. Indeed, I didn't even tell you what the actual boundaries were in the first place, so it would be a bit pointless to do so. But I'll talk about the cycles. I'll talk about what the differential looks like, or at least indicate that, and then say something about how you build a representing object. So I'll show you some more pictures of things, of diagrams. Okay, so firstly, so these witness cycles, I mean, if you remember, what were the R cycles for a multi-complex? So, well, it was an A0 such that there exist a bunch of other I's, sorry, a bunch of other A's, A1 up to AR minus 1, such that exactly these equations were satisfied. So all we've done here in writing down instead the witness R cycles is to make a choice of this A1 up to AR minus 1. So an R cycle was an A0 such that there exist these higher A's satisfying exactly these relations. And here we've made a choice. So if you like, the A1 up to AR minus 1, they're witnessing how A0 is an R cycle. So instead of requiring the existence of witnesses, we've specified a choice of witnesses in our witness R cycles. So that's kind of the obvious thing to do. An R cycle was defined by, it's an A0 such that there exists some choice of these witnesses. Let's just take a choice, and that's a witness R cycle. So that's a natural thing to do. And I mean, I only specified this on objects, but it extends in an obvious way to morphisms to give a functor. And I've done this for the general multi-complex case, but you can just restrict to n multi-complexes for any n. So we have these witness cycles as functors on any of the categories that I've described. Okay, so here's a picture. In fact, it's kind of the same as the previous picture, the last one that I showed you, but with some stuff scribbled on it to indicate what's changed. So if you remember, I got as far as sort of telling you about the 3 cycles that you have, well, in a general multi-complex, I guess. So we had then an A0 such that there existed an A1 and an A2, satisfying some equations that are kind of indicated here. And now the witness 3 cycles in this picture. So now instead of requiring the existence of an A1 and an A2, we specify a choice of such an, oh, sorry, didn't mean to click that. we specify a choice of such an A1 and an A2, and a triple like this is a witness 3 cycle. So the A1 and the A2 acting as a choice of witnesses. And the other thing that's changed here is that, and I think this is probably all I'm going to say about what happens to the differential when you do it for these witnesses. So now we have to specify, well, here it's the delta 3, the differential on this 3rd page of the spectral sequence. And we have to specify it on witness cycles now. And it should take a witness cycle to, well, a class of a witness cycle to the class of a witness cycle. So what happens is that, and here's the 3 cycle that was the image before, and then we can specify witnesses to how that is actually a 3 cycle. So you get explicit formulas for the differentials on these witness cycles, and the classes are taken modulo suitable witness boundaries that I haven't explained to you. I won't give formulas for. Okay, so that's a picture that's supposed to give you some information about witness cycles. And then there was this story about representing objects. So I'm going to show you a couple of pictures related to that. So, so this is a representing object for witness cycles in the bicomplex case. So this 2 upstairs means we're doing n multi-complexes for n is 2. So we're doing bicomplexes. And, well, any r you like, r bigger than or equal to 1. So in the bicomplex case, so remember that's the thing we'd already done previously, it's sort of easy to draw pictures for these representing objects for every r. So this is the one for the cycles. It's just this staircase bicomplex, r horizontal steps. So I suppose I should say what this means. So this is supposed to be a bicomplex. Every spot here, every bullet, and also this star, which is just indicating the source bi degree here. Every spot is just a copy of big R, the underlying ring or free module of rank 1. And every arrow in this picture is just an identity map. So that's what this picture is supposed to mean. So it's a very simple bicomplex where you have a single copy of R in the indicated bi degrees, 0 everywhere else in the picture, of course, and some identity maps. So the differentials are identity maps where the arrows are indicated, and they're 0 everywhere else. So in the bicomplex case, I can show you a witness object for the R cycles. I haven't included the picture here, but one can also do the witness boundaries very explicitly in that case. The representing object is something called a box under the stairs complex. So it kind of has a staircase and a box somewhere and then some more stairs. In any case, one can really explicitly do all these representing objects in the bicomplex case and just sort of understand them with simple pictures. When you put in the higher Ds that you have in the multi-complex case, things get a bit messier. So that's what's on this next page. So I've gone to n equals 3, so just up one step in the multi-complex structure. So in other words, I now have a D0, a D1, and a D2, but no higher Ds. And I've only done these pictures for very small r now. And indeed, I won't tell you everything about what's going on even in these ones, but they're just really here to indicate that things get a bit more complicated. So even for one cycles, so in the bicomplex case, we would have just had a single horizontal step. So just this single thing, this little bicomplex here with a single D1 in it. As soon as we go up a step with our structure maps, things have got more complicated because, well, firstly, we have some non-zero D2s, which are these longer arrows, but also D1 squared is no longer 0. So we get all these iterated D1s, and we get now an infinite complex continuing to the left because D1 can be iterated and doesn't have to ever become 0. So anyway, this is a representing object for the one cycles in that case, and then this thing for the two cycles. And really, these pictures are mainly meant to convince you that it's not a good idea to just try and draw the representing objects and do everything very explicitly. So that was possible in the bicomplex case, but the representing objects are going to get quite complicated to understand in this manner when you have all these higher structure maps, the higher DIs. So what do we do instead of that? What you can do is just construct the witness cycles by an iterated push-out construction. So you don't need to sort of explicitly give them by formulas or have in mind very explicit pictures of what these complexes or multi-complexes actually look like. So let me just say a little bit about how you do this with the push-out thing. So, well, firstly, how do you start? That's easy. So the zero witness cycles are just the zero cycles, which is just the underlying object. So you're just trying to represent picking out an element in your object. So that's given by maps in of a free object on one element. So that's how you start. And then what about the witness one cycles? Well, they're just also the one cycles. They're just given by the one cycles are given by the kernel of D0 on representing objects. What that means is that you take this kind of push out or this co-kernel of a map that's sort of representing D0. So that gives you the one cycles, and then once you've got started, you can define the representing object for the R cycles recursively. So it's just a push out. You imagine that you've already constructed the R-1 cycle, so that's what's living down here in this diagram. And then I won't go into details of things, but I mean, roughly what you're doing here is you're taking the R-1 cycles and you're adding in one new generator in an appropriate by degree subject to the new relation that you need in the witness R cycles. So that's what this push out diagram is doing. It's constructing the R cycles from the R-1 cycles and one new generator, one new relation. So there's quite a straightforward way to get this representing object by this iterated push-out construction. Okay. And then similarly, I mean, I haven't told you about the BW really, but you can similarly define the witness boundaries object and the map that goes between the witness cycles and the witness boundaries. Okay, and then, well, I haven't really told you enough to know what's going on here, but I hope I've given you some kind of flavour of it. So what I'm doing here is specifying the I and the j. So for each, so I'm thinking about an n can be anywhere between 2 and infinity, because I'm thinking about the category of n multi-complexes, anywhere from bicomplexes up to multi-complexes. And I'm thinking about stage R of the associated spectral sequence. And so for each n and r, I'm going to specify my two sets of morphisms, my I and my j. So the j I have kind of told you about completely, because j is just a map from 0 into the witness cycle object, which I've described for you. And then I've kind of mentioned the data that goes into the I. It's this map at the level r+1 from the witness cycle object to the witness boundary object, which I haven't described this or this, but I've kind of indicated what kind of thing they are and what they do. And then the point is that, well, these sets, or more or less these sets, the I and J0 together with JR, those are the sets of generating cofibrations and generating trivial cofibrations for a model structure on this category of R. So I've written multi-complexes, but this of course should say n multi-complexes, because I've kept the n everywhere. And you can probably see that from the sort of what's going on with the generating trivial cofibrations here, that this is going to give you a model structure where the fibrations are characterized by, well, surjectivity conditions at the level of, well, the level of the object itself and at the level of the witness R cycles. So this was this sort of variant model structure that I mentioned earlier, where the fibrations are characterized by surjectivity conditions, in particular on something related to cycles, namely the witness R cycles. And then if you want the one that was actually the one that I stated as theorem earlier on, what you can do is kind of take these things that I've given you here and take unions with the lower j's. That's roughly what's going on here. In any case, you can kind of modify the sets I and j that I've specified here by taking appropriate unions of them. That gives you the model structure that I stated in the theorem. So that was the one where, when both cases you have weak equivalences given by the ER quasi-isomorphisms, and this one here will give you the fibrations characterized by surjectivity conditions on the I page of the spectral sequence up to the R page. Okay, and then finally, I wanted to say something about comparing some of these model structures. So that's what this theorem here does. So let me just explain what's going on here a little bit. So we've given ourselves an n and an L now, between 2 and infinity, and we're comparing the category of n multi-complexes with the category of L multi-complexes. So different sort of stages in the structure, varying the n. And we're fixing the R, so the stage of the spectral sequence is fixed. So what I've done so far is I've given you a model structure for each n and each r of described a model structure on these categories, and now we're comparing those model structures for fixed R but varying N. And well, the statement is that there's an adjunction which is a Quillen equivalence. So if you fix the stage of the spectral sequence but vary the N, then you get Quillen equivalent model structures. And I'll just end with a couple of comments about that. So, I mean, the main idea of how to do this is that there's a way of thinking about N multi-complexes as modules over a suitable DGA. So you have a DGA Cn, and you work in vertical bicomplexes, and you can think of multi-complexes as the modules for that differential graded algebra. And then you can relate Cn with Cl, and that allows you to specify the functors that are appearing here. Those functors can be thought of as restriction and extension of scalar functors. And maybe just to comment on this finally, I mean, this is sort of maybe what you would expect, or at least maybe you would expect a special case of this to be true. And indeed, we sort of know a special case of this sort of classically. So if you could think of putting N is 2, so bicomplexes on the left, and L is infinity, so multi-complexes on the right. So we'd be comparing bicomplexes and multi-complexes, and we could do that for R is 0, so the sort of the 0 model structure where the equivalences just are usual quasi-isomorphisms with respect to D0. And we would be saying that bicomplexes then have that, in terms of that homotopy theory, they have the same homotopy theory as multi-complexes. And remember, I said that they're the homotopy coherent version of bicomplexes. So that's something you would expect. You would expect bicomplexes and the infinity version of them to have the same, well, Quillen equivalent model structures for that R equals 0 model structure. That's kind of the classical thing. So this result you could think of as generalizing that in a couple of ways. It says that the same is true for all these different R model structures as you look at different stages in the spectral sequence. And it also says that they're all Quillen equivalent for all these intermediate categories, not just bicomplexes and multi-complexes, but all the truncated versions in between as well. And I think I'll stop there. Thank you.